Okay, so now you're being recorded. Does anyone have any specific questions they'd like to ask?
I have one on
Yes.
the hydrate lab. When we get to the end and we're doing an experimental formula, what's how do you want me to write that? Because the final numbers that I got were things like 1.7 to 1 moles. So should I round up to just
Nope. Nope,
No?
you did not.
Okay.
So
So
what
how
you
would
should
I
do-
write that then in formula form?
just do that.
Okay, perfect.
Now, if it were a pure substance, it would be that or that.
Mm-hmm.
Now, this, of course, could be written as a 0.5 H2O. Or it would be, that. So if you didn't come up with what we have when they're pure substances, one of your jobs in your discussion is to explain the difference.
Yeah.
So what do you think?
Honestly, I wasn't sure yet. I wasn't expecting to get such a big difference in accuracy. I know I had trouble getting the actual gypsum into the tubes. That was the first one that I filled, so I think maybe my numbers were off there, but I don't know.
Could be a lot of different things.
Yeah.
Let's say, for instance, you started off with 1 gram, which is pretty hard to do. But let's say you just happen to start with 1 gram and you heated it up, and afterwards there was 0.82 grams. Now that would mean that you had 0.18 grams of water, right?
Mm-hmm.
Okay. So if you take your 0.82 grams and multiply by 1 mole per 136 grams, you would get, I can't do this one in my head, but I know the answer is going to be smaller than 1, right?
Mm-hmm.
It better be. So 0.00603, and this would only have 2 sig figs, and you have your 0.18 grams. This one's going to be a lot easier. Now, this, of course, doesn't make sense unless I give you some sort of indication that that's what I'm talking about.
Uh-huh.
This one is going to be 0.0100, something like that.
Yeah, that's what I got.
And actually ends up on my calculator being 0.009994, which is pretty much 0.0100.
Yeah.
And so here you would have 0.009994 moles of H2O over 0.00603 moles of calcium sulfate. And let's see what that ends up being. So that ends up being calcium sulfate 1.7 H2O. Okay, so
Same.
Are these the numbers that you actually had?
Pretty darn close. You were exact on the H2O, and my calcium sulfate was 5.8 instead of 6.0.
And I was getting the same kind of numbers, and I thought I did it wrong.
Right?
Well,
Yeah.
So I thought I thought it's because my measuring device wasn't accurate enough.
Right.
But if that's the numbers we're supposed to get, good.
It may be that your numbers are off. So let's take a look at this. Suppose that when you measured this, this was not actually 0.082, but it was 0.80. Now, most of us would look at these two numbers and say that they aren't that different. Agreed?
Mm-hmm.
And that would make this 0.20. And let's see how that would change everything. So here, if this was 0.80, I'd get 0.00588. And if this were 0.20, I'd get 0.011098. And if I took these two numbers and worked with them, let's see what we get here. I get 1.9. So
Mhm.
you see how just a 2-number difference here can make a 2-number difference here. 0.2 of a difference here. So one of the things I would caution you about is there's built-in experimental error here just because of the limits of your scale or your balance. If your balance did a better job, maybe you could do a better job, but it doesn't. And so you have to be aware of that. Secondly, you can see that this amount of a difference made this amount of a difference. And maybe that's not enough to actually justify this number. And so you think about other reasons too that may account for the difference. So if it's not just a matter of your scale or your balance, what else could it be?
I was hoping you'd tell me.
Well, I want you to think about it.
Well, I get the precision. That was the one thing that I was going to discuss in the discussion part of my lab, but I didn't think it accounted for that much of an error either. So I was getting those numbers with the gypsum. So another thing is maybe I didn't heat it long enough to get out all of the water.
That could be a second explanation, right? Did you heat it to where the mass didn't change?
Yes. And I got to the point where I even held it over my stove and watched for more condensation on the inside. And I got to the point where I didn't see any more.
That's good, because if you see condensation on the inside and you leave it there, that is mass of water you're including with your dehydrate that doesn't belong. So the H2O has to be gone completely.
Yep. I kept holding it until every last bit was off of the glass part.
Now you're making me nervous when you hold your fingers up like this and say, I was holding it.
With a pot holder holding the test tube clamp. And then I have an electric stovetop, so at least it wasn't a full flame.
Oh, electric stovetops don't work very well.
No, it took forever.
That's
And
why. That's why if you have an electric stove, you just stick it in the oven and you walk away.
I put it in the oven for over an hour. And then to test one, I took the gypsum and just put it on the stovetop just to make sure. And there was still condensation coming out. So
what temp did you have the oven at?
400. And then I upped it to 450 because my oven's a little sketchy on temp.
Yeah, I would have put it on broil.
Ah,
Let
okay.
it go.
Yeah.
You could even stick it under the broiler. Not many people use their broiler.
Yeah.
But what else could it be? There's still a third possibility.
Contaminated sample?
Yes, only I wouldn't use the word contaminated. I would use the word it's a mixture. Maybe it's a mixture of two things. Maybe it's a mixture of these two things, but it's mostly that one. So, Greg, yes, contaminated with one of the others. So those are the kind of explanations that you offer. And the reason I really like this lab is because it never comes out to be 2 and it never comes out to be 0.5. And you're supposed to get real results and you're supposed to talk about them in a real manner. And so you talk about the limits of your equipment. You talk about the fact that it may be impure. and you talk about maybe experimentally there may be something that you didn't quite nail. Okay, so there's
Gotcha.
lots of different things that you could offer here for explanations. And then naturally, after you write a discussion like that and someone comes back and revisits your lab, they say things like, well, shoot, if she wrote down that it didn't work in the oven, I'm not using the oven anymore. I'm not using the oven.
Uh-huh.
If I repeat this experiment, I'm going to use the stovetop or get an acetylene torch or something,
Mm-hmm.
So you don't have to, in your discussion, say, so here's what I do different next time. If you wrote down the things that didn't work this time, guess what? You're not going to do it next time. You're going to do something different and something better. So I'm not a big fan anymore of writing down, here's what I would change, because when you write down what didn't work, clearly those are the things that you're going to change. So those are really good, important points. And I'm glad you brought this up. And hopefully you now have a place to hang your hat on your discussion.
Yep. That's the last part I have to do. So good deal.
All right. And if this was the only help you needed tonight, I won't be mad if you sign out.
Thanks. I appreciate it.
All right. Does
Bye.
anyone else have a question?
I had a question about I'm sorry if someone asked this already, but about like actually conducting an experiment. So it says in this part, it says allow to cool, mask the test tube, and repeat till all formulas of hydrate have been removed. And it's like, how do you know when to stop?
That's a great question. And the answer is, I'm going to make you think about the answer. So imagine you have a sock that's wet that you just washed and you throw it in the dryer. How do you know the sock is dry without just touching it and saying, oh, it's dry? And you do have a balance laying around. You do have a ruler laying around. You have all that stuff you use for chemistry. How do you know your sock is dry?
It's gonna be a lot lighter.
Yes, it will be lighter. How do you know it will be lighter?
I mean, it's gonna weigh less than it did before.
Just say because the water left. The water left. It should be lighter, right?
Yeah.
Okay. How much lighter will it be?
Almost half as much, maybe. I don't know.
Who knows, right?
Yeah.
That's one of those who knows. Well, let me ask you this. So you take it out of the dryer and it feels lighter.
Hmm.
How do you know it is lighter?
Because you probably felt it when it was wet.
How about because you weigh it?
Yeah.
That's how you might know it's lighter, right?
Okay.
Because you weigh it. But how do you know all the water has left?
Hmm.
Well, let me ask you this. If the sock had any water left in it and you put it back in the dryer and you pull it out, what happens to its weight?
It's gonna be the same.
If there was water left, if there was water still left in the sock,
Oh, it'd get even lighter.
it would get even lighter. Okay, so you find out it gets lighter. You throw it back in the dryer, you let it cool down, you pull it out, and now the mass is the same as that second time you weighed it. What does that tell you?
That it's completely dry.
Right. So you have heated the sock to a constant mass.
Okay.
You with me?
Yeah, I got you.
So it's the same way with the hydrates. What you do is you weigh it before and after. So when you weigh your hydrate, so let's say you get 0.97 grams of your hydrate, and you put it in your test tube, and all together, let's say that this weighs 20.97 grams, which means that the test tube is 20.00 grams. Of course, I'm inventing a number that's easy for me to subtract.
Hmm.
But let's say that that's what you get, and you heat it, and you weigh the whole thing, and instead of 20.97, you get 20.90, and you heat it again, and you get 20.91, which makes it look like it got heavier, right?
Hmm.
But in reality, it didn't get heavier because that last number is just an educated guess according to your balance. So 0 and
Yeah.
a 1, for all practical purposes, are the same thing. This, I would say, you're done. On the other hand, if you heated it again and you got 20.80, when that number changes, I'd say, okay, that's significant. Maybe I need to heat it a little more.
Okay.
And then if you do this and get 20.80, then you're done. Does that make any sense?
No, I get it. That makes sense.
Okay. So the important things are when you heat it and cool it and heat it and cool it, you need to let it cool down until you can handle it comfortably. If you can't handle it comfortably, it's too hot to weigh for two reasons. It could damage your balance or your scale. And that's the less significant reason. The more significant reason is you could burn yourself.
Yeah.
Okay. And then another significant reason is that hot things weigh less than cold things.
Oh, okay.
And the reason they do is because when you have hot things, air hits the object. And when the air heats up, it becomes less dense and it rises. So when the air rises next to the test tube, it will raise it up, making it weigh less.
Mm-hmm.
So this is why when you weigh yourself, you should be hot instead of cold because you'll weigh less.
Okay. I'll keep that in mind.
Okay, so does that help you at all?
Yeah, that makes sense.
Okay, great.
Also a little less formal. I don't know if you have any like advice for getting the compound from your scale into the test tube, because I feel like a lot just kind of like fell out and I tried to get back in, but like I feel like that might have.
You know, did you see the video about how I put the stuff in the test tube?
No, I didn't know there was one.
Oh yeah, the module Q&A, usually people ask about those things.
Yeah.
So if you go to the Q&A, you find out, but this is the way you do it. Piece of paper that's folded twice. And you put the you put this on your balance. You put the powder in here. And then once you weigh the powder, you take this and you make it like a little funnel and you pour that into your test tube.
Oh, okay.
And so a lot of these labs, especially if you look at the module for that particular day when I release the lab, you'll see me talking about the lab. So if you go back and look at today's module, which I haven't posted yet, but the afternoon module, you'll see me talking about the precipitation lab that I put out there today.
Okay. All right, we'll take a look. Thank you.
Okay, you bet. Who's next? I feel like I'm on a roll. Okay, if someone doesn't say they're next, then I'm going to start talking about today's lab. Okay, now I'm going to start talking about today's lab. Today's lab, we're going to do a precipitation lab. And a precipitation lab is when you have two solutions. So this has sodium ions and chloride ions in it. And when you have these solutions, these ions are just floating around in water. Each one of these is surrounded by water molecules. So in a precipitation reaction, here's what happens. So we're going to mix these two together. And of course, when I mix these two together, I need a bigger container to put them into. But what will happen is that the silver and the chloride will bunch together. And they actually form a solid called an ionic solid because it's made out of ions. The nitrate will not bond to anything else, and neither will the sodium. So this is called a precipitate. And the precipitate is a solid formed from two previously dissolved ions. And the reason I say previously is because they're not dissolved anymore. So that's a precipitation reaction. Let's take a look at a real precipitation reaction, okay? So I'm going to do a new share. I'm going to go to my Firefox, and I'm going to go to AgCl and AgNO3, and then NaCl reaction. And what we're going to do is we're going to look for a little video here. And here we go. This might be a good video. Hard for me to tell.
In the double displacement reaction of silver nitrate and sodium chloride, we have a solution of silver nitrate, which is colorless. We will add a solution of...
Okay, so in that solution, the silver ions and the nitrate ions are not together. They're separate from one another, floating around in solution. The reason you can't see them is because they're the size of atoms, and atoms are too small to see.
Of sodium chloride, which is also colorless. When the sodium chloride solution is added...
Okay, so what you don't see here is that there's an eyedropper above the solution that has dissolved sodium chloride in it. And you all know what a dissolved sodium chloride looks like. It looks like water. So when you put one drop of that sodium chloride in that solution, look at what happens. You get this stuff that looks cloudy. The solution is no longer clear. Clear means you can see through it. Cloudy means you can't. So this is a precipitate. Now, that white stuff is a solid. And you might ask, well, if it's a solid, why isn't it at the bottom? And the answer is it will be eventually. It has to settle to the bottom. It's kind of like when you jump in a mud puddle and all that mud is everywhere and it's swirling around and it looks like almost like a decent coffee with milk in it. And then you leave that mud puddle and you come back 10 minutes later, all of the dust is settled and you can see through the mud puddle now, and it's not a mud puddle anymore. That'll happen to this also.
To the silver nitrate solution, a white precipitate, insoluble silver chloride is formed.
So that's a pretty cool thing that's happening there. And right here, they're showing you how you write out the product of that reaction. So that's what you're going to be practicing with this particular lab. Now I'm going to change my share. Back to this. Okay, so what are the things that you have to do? Is you have to get the right bag. So this is the bag. It also comes with some test tubes in it. My test tubes are wet from using them this afternoon. And you don't want to use wet test tubes in this lab if you can avoid it. So the best way to clean these out is to use your water bottle like this, and you put a little water in here. And I'm pouring the water into a beaker. Now, the reason I'm doing all of this right here at the table is because I'd like to do it in my sink, but I don't want to set up all my computer stuff around the sink. Does that make sense? Okay. So now to dry the test tube, I'm going to try and tap the water out, use a paper towel, and just thread it into the opening like so. Okay. Now you also want to find a spatula, which should be in your box. The spatula looks like this, and it may not be with any package, but just kind of loose in your box. We're going to need that. Okay, so I have a dry test tube here. And I only got 4 test tubes to work with, not 5. So, oh well, just means I'll have to work a little harder. So I'm drying these test tubes now. Make sure you don't stick the paper towel all the way to the bottom of the test tube and shove it in there with that stirring rod. Because if you don't leave a little bit of the paper towel hanging out of the end, you won't be able to pull it back out. Okay. Okay. So I've got my clean test tubes. And let's see, where's my other beaker? That's probably in the sink. Okay, so what I'm going to do with this, because I don't want to walk away, is I'm just going to pour this out into my dirty paper towel. Okay, there. Okay, so I do want to show you how you test for solubility. So I'm not going to tell you which compound is which. I'm just going to show you how to test. So here I have a test tube, and I'm going to put some of my solid in there. Okay, so I'm going to open this up, and I'm going to take some of the solid out. And so I don't know, can you see the solid here? So I'm not using all of the solid, just some of it. And I'm going to put it inside of my test tube, like so. So I've got a little bit of solid in my test tube, and maybe if we move this over just a little bit, can you see down the bottom of my test tube that it looks like there's white solid in it? And here's a test tube with nothing in it. So you can see the wood beneath the test tube if I hold it just right when there's nothing in the test tube. And here you can see the solid in the test tube. So now I'm going to add a little bit of water to this. And you can see how much water I've added. You know, to give you an idea, here's a cork that came in the test tube. And what I'm going to do here is I'm going to take my stir rod, and I'm going to put it inside of the test tube, and I'm going to twirl it. Okay, so I've twirled it. And now when you look down the test tube, you see how you can see the wood table beneath? And when you look at this from the side, that has dissolved. Okay, so let's clean off our stir rod, paper towel. I don't want any impurities on that. And let's see what happens when I do this with another one of these. So here's one. Not going to tell you which one it is. I'm taking a little bit of the solid and I'm putting it into the test tube. So when you look in the bottom, you can see the white powder in the bottom of that test tube. And now I'm going to add a little bit of water to that. About the same amount of water I added to the other one. And I'm going to twirl this again. And we're going to take a look at this, and you see how it is cloudy. That means that this stuff did not dissolve. So this one did not dissolve. This one did dissolve. So this dissolved. This one did not. And you might wonder, did you add enough water? So you can add a little bit more water and see what happens. So I added quite a bit more water. I'm going to put my stir rod in there. And when we take a look at that, do you see how it is still cloudy? That means it did not dissolve. Okay, so this one did not dissolve. So you're going to do that with all 5 of these. You're going to determine which ones dissolve and which ones did not dissolve. Okay, now that that's done, let me show you something else. So I'm going to take one more of these. And I'm going to make sure my stir rod is dry and clean. I'm going to take a little bit of the solid here, put it in a test tube, add a little bit of water, stir it. And this one looks like it didn't dissolve, right? So just like with the other one, I'm going to add a little more water and see what's up. So this time I didn't go really crazy with the water, but you can see it dissolve. Can you see the grain of the wood beneath the test tube? Okay. So this one dissolved and so did this one. So you're going to do that with all 5 test tubes, all 5. And the ones that dissolve, you want to keep those around. The ones that don't dissolve, you want to put them off to the side, get rid of the solution, and move on. So I'm going to change my tabletop here. So the first step is 1, see if any of the solids dissolve in water. That's your first step. See if any of the solids dissolve in water. Are there any questions about that? Are we good to go?
We're good to go.
Okay. Jessica, we're good to go? You can give me a thumbs up. Greg, are we good to go? Okay, thank you. The second step is, let's say that we have 2 of these dissolve. I'm going to call this A and this one B. And these are not soluble. So remember, these are going to be cloudy. These will be clear. So the second step is you take A plus B and you see if it gets cloudy. Because if it gets cloudy, it's a precipitation reaction. Now, what happens if you get 3 of them dissolve? Well, if 3 of them dissolve, I got A, B, and D here. You want to do A plus B and see if you get a precipitate. This is my abbreviation for precipitate. You want to mix A plus D and see if you get a precipitate. And you want to mix B plus D to see if you get a precipitate. So you want to do 3 reactions here. Now, what happens if you get 4 of them? A, B, C, D. Then you do A plus B, A plus C, A plus D, B plus C, B plus D, and C plus D. And if all 5 dissolve, well, you know that's not going to happen because I already showed you one that didn't dissolve. So you want to mix things together. Now, here I have these 2 that did not dissolve. And again, if I had another one of these, what I'd have to do is make these solutions again to do what I'm going to do next. So let's pretend this is A and B, and let's see what happens when I add A to B. So here we go. So do you see what happened there? That is a cloudy solution. And that's a precipitation reaction. So you want to mix all possible combinations and see if you get a precipitation reaction. Right now, I'm rinsing out my test tube. So let me write down here. Number 1, see if any of the solids dissolve in water. 2, mix pairs of soluble solutions to see if you get a precipitate. That's the procedure. So are we good on the procedure, everyone? Okay. So let's take a look at the actual lab description. And so I'm going to change my share to the lab itself. So I'm going to Firefox. We're going to go here. We're going to go to the class. Okay, here. And I don't want to go through this whole thing and read it with you, but I will refer to some of the things that are described in the description of the lab. And ask questions if you have any. So here's your lab, your precipitation reactions. You're supposed to submit images of the lab write-up. So background or introduction, if you will, same thing. Introduction, safety, procedure, data, calculations, results, discussion. So that's what you're gonna do for your lab write-up. I want an image of your water solubility test. So you're gonna test 5 things here. And I know you only have 4 test tubes, so show me 4 test tubes that show me whether or not something dissolved or not. And when you're using these test tubes, you want to write in that little white label that you have on the test tube. I have one of these test tubes that does not have a white label. So in that case, I would use masking tape and I would write on the masking tape. Okay, so I want an image of all 4 of those test tubes side by side by side to see what the results look like, what you're looking at. I want images of all the precipitation reactions. So what I mean by images of the precipitation reactions, I want to see the test tubes with precipitate in them. If you mix 2 test tubes together and nothing happens, then that is not a reaction. And then I want the answers to the assignment. So let's go through the background very quickly here. So this talks about how things behave when they dissolve. This is a rather tiny image, but on the left, you're supposed to see sodium ions next to chloride ions in a very rigid 3-dimensional structure. Here, it's only 2-dimensional because it's really hard to do 3D on paper. So on the left here, we have a solid. When you add water, what happens is those ions separate from one another, and each ion is surrounded by water molecules. So where those ions used to be neighbors before, now they're not neighbors at all. That's what happens when an ionic compound dissolves. The ions slip away from one another and are then surrounded by water molecules. Okay, so that's a drawing of sodium chloride dissolving. This can be written 2 ways. Does everyone see I have NaCl solid turns into Na aqueous plus Cl aqueous. Aqueous means dissolved in water. Below, you can see I have NaClS turns into NaClAq. Those 2 equations mean the same thing. And so we have to understand that when we see AQ behind a ionic compound, it means that the ions are not actually together anymore. They are separate from one another, floating around in water. So the above way of writing it is a better description. The lower way of writing it is faster. And how do scientists do this? They use the lower way. Now, below we have a list that is incomplete, but a list of how to tell if something will dissolve. So ionic compounds with lithium, sodium, potassium, ammonium, nitrate, or acetate are water soluble. that means if the formula has one of those things in it, it will dissolve. If the ionic compound has chloride, bromide, iodide, they are soluble unless combined with silver ions or lead-2 ions. So this is not a complete list, and I don't want to go through the whole thing, but I do want to look at below. Below, we have a precipitation reaction. So notice on the above, we have this NaCl. The sodium ions are separated from the chloride ions. And the reason this is soluble is because sodium ions are soluble. Any ionic compound with sodium ions are soluble. Below, we have nitrate and silver ions. And why is this soluble? Well, if we look at the rules above, it says that nitrates are water soluble, NO3. So even though there's silver in here, which tends to not be soluble, this is soluble. Now, when I say plus and this arrow here, this image in the middle is when they just start mixing. So these ions are floating around in water. And what's going to happen is the silver ions are going to run into the chloride ions and they stick together. So on the far right, can you see all the silver ions and chloride ions at the bottom sticking together? That is a solid. And if you take a look at the nitrate ions and the sodium ions, they don't stick together. They're still dissolved. So how do we write this reaction out? And here it is. NaCl aqueous, silver nitrate aqueous gives you silver chloride solid because it's no longer soluble. It's a precipitate. And NaNO3 aqueous because that's still dissolved. Now, what is the net ionic equation? The net ionic equation does not include those ions that are still dissolved. So sodium ions and nitrate ions are still dissolved, so they're not included in here. So here, for this NaCl, we don't include the sodium because it's still dissolved. And that's your net ionic. So what are the things that are not in your net ionic equation? They are things called spectator ions. So in this case, the sodium ion and the nitrate ion are spectator ions because they're dissolved to begin with and they're dissolved to end with, which means they're not really doing anything. They're just watching. All right. So safety. Everything used in this lab is not toxic. When you're done with the solutions, you can pour them down the sink with running water. Are we okay on safety? How about you, Greg? Are we okay on safety here? Thank you. Okay, so here you can see that for the solubility, I say, test the solubility of table salt in a micro test tube. And the reason I want you to start with table salt, even though I don't provide it, is because you know table salt is soluble. If you use too much table salt and not enough water, it will not dissolve completely. So this is to give you an idea of how much to use. And then you got to label your micro test tubes, test a pea-sized amount, maybe a little less than pea-sized, add about 1 centimeter of water, and see if it dissolves. So does everyone understand that the solubility procedure can be whittled down to see if each of the 5 things dissolves one at a time? Capiche? All right. Precipitation. For those substances that dissolve, mix pairs together to see if a precipitation reaction occurs. Okay, so we only do that for solutions where it does dissolve. The data, you're supposed to make a table with the name of each compound, its formula, and indicate the water solubility. So let's take a look at one of the compounds, okay? I'm going to change my share screen. So one of the compounds is calcium carbonate. And I'm going to go back and look at the question again. Make a table of the name of each compound. So calcium carbonate. Its formula. And indicate the water solubility. So here's the name. Here's the formula. And here's the water solubility. So what we're doing here is we're making a table and we're making a prediction of whether or not it will dissolve. Let's see what we can find out about calcium ions and carbonate ions. And we're going to look at the rules above. So in the middle of the page, you can see the rules. Are there any rules about calcium ions? Do you see this one right here? This does have calcium ions in it. So this says compounds with sulfate
Tony,
are
back your camera
soluble
out.
unless combined with calcium, right?
Your
Does that
camera's
apply-
on your elbow.
What's that?
So your camera's on your elbow.
Oh, okay. Sorry about that.
It's okay.
I need to change my share then. So let's take a look here at the lab. Thank you for letting me know about that though, because there we go. So do you see how that says calcium in it? But the formula we're looking for is CaCO3. So that doesn't apply here. So this list here are things that are soluble. If they're not on this list, what's our assumption? The answer is not soluble. So we're going to say for this guy, name, formula, water solubility, not water soluble. So you're going to do that with all 5 of them. You're going to predict whether or not it should have dissolved or not. Okay. Number 2. Do these compounds, all of them, conform to the solubility guidelines given in the textbook? And here, if we test this and it does not dissolve, we'd say, yeah, it does conform. And we're supposed to give a brief explanation. And for this one, we would say, so this is number 2, calcium carbonate does not dissolve. And this is because it's not covered by the solubility rules. Hence, it's not soluble. So that's what you would write for the explanation for number 2. 3, for those compounds that dissolve, show what happens 2 ways. So do you remember for sodium chloride, I said you could do this or this. So you have to do these for all of the ones that dissolve. That's number 3. Number 4 says draw a diagram of what happens on the ionic level. So here's what I did for this one. So this is a solid plus H2O. And so here, where we used to have all of the ions packed together we now see that they are separated. So this would be number 4 and this would be number 3. So I'm going to give you a moment to catch up on those. Number 3 asks you write down them dissolving in 2 different ways. And number 4 was draw a drawing of what happens when it dissolves. And number 4 says only do this for one of the ones that dissolves. You don't need to do it for all of them, just one of them. Do this for all. And hear this, do this for one. Do this for all, do this for one. Are we good? Okay, let's take a look at number 5. Number 5 says number 5 asks you, how much wood could a woodchuck chuck if a woodchuck could chuck wood? Okay, that's not what number 5 says. Number 5 says, for each precipitation reaction, write out the chemical reaction, the net ionic, the spectator ions, and draw a figure. So I'm not going to do that right here. What I'm going to do is I'm going to show you the lab. So number 5 says chemical reaction, net ionic, formulas of the spectator ions, and for one of the precipitation reactions, draw a figure showing what happens on the ionic level. So let's look at above and show you that this is what I've shown you here. So this drawing is what's happening on the ionic level. There's the reaction equation. There's the net ionic. And here we have the spectator ions. Now, what I'm going to do here is I'm going to take you methodically through what is happening here and how we figure out what is happening. So notice we have sodium chloride aqueous and silver nitrate aqueous being combined together. So I'm going to write this down on a piece of paper, and then I'm going to bring your attention to this in just a moment. Now, the reason the sodium chloride is soluble is because things with sodium ions dissolve. The reason the silver nitrate is soluble, AQ, is because the nitrate ions make things dissolve. Okay, so now I'm going to change my share. There we go. So we have this that is aqueous and this that is aqueous. And let's see how we can figure out everything just based on these 2 things and solubility rules. So we know that when sodium chloride dissolves, you get sodium ions and chloride ions. We know that when silver nitrate dissolves, you get silver ions and nitrate ions. Okay, now our solubility rules say that this is soluble. And they say that this is soluble. So compounds with sodium in it are soluble. Compounds with nitrate in it are soluble. So since these are soluble, nothing happens to them. So they end up right on the other side, just as they were before. Now, when we mix these 2 things together, we do see a solid. If these 2 are not part of the solid, then what has to be part of the solid? These 2 guys. So that's how we write the solid that forms. So you remember that video when the drop was dropped into the test tube and it turned really murky and cloudy right away? That was silver chloride. So this is what we might call the total ionic reaction. So these ions are written separately because in solution, they are not stuck together. These ions are written separately because in solution, they are not stuck together. These ions are written separately because they're still not stuck together. These ions are written together because they're stuck together in a solid.
So what would take the sodium chloride to bond together to make salt? I mean, right now you got them both. Shouldn't they both form to make salt?
No, they're
Sodium-
dissolved in water.
And they don't precipitate out into, okay,
No, they don't. The only way to get them to precipitate out is not through a precipitation reaction. It's by evaporating the water.
oh, okay,
And that's not a precipitation reaction. A precipitation reaction is one where the ions want to bond together so strongly that they will do so even though there's water around. And you know sodium chloride does not spontaneously appear out of water unless you
Right.
evaporate the water. So that's not a precipitation reaction.
that makes sense, okay.
Okay, cool. Good question. So here, if we take a look, the spectator ions are the ones that don't change in this whole process. So sodium and nitrate. Now, if you want to write the net ionic equation, here's how you always start it. So how am I starting this? I'm starting it with the precipitate. So I'm starting it with the solid. Now, how do I finish it? I look at the solid and I ask, what aqueous ions came together to form this solid? We had silver aqueous ions and we had chloride aqueous ions. So these two aqueous ions, which used to be in separate containers, were forced into the same container. They saw each other and it was a match made in chemistry. They stuck together. The end. Okay, so this is the net ionic. These are the spectator ions. How do we write out the reaction? Well, we definitely want to put the solid in there. But what do you do with the spectator ions? And the answer is you write them together. But when we write them together, how do we indicate that they're still dissolved and they're not a solid? And the answer is you put AQ behind it. So here's the reaction. Here's the spectator ions and here's the net ionic. And sometimes you want to write all the ions out like this to help you decide what's going on. Okay? So that's a lot to sink in right now, but I don't expect it to sink in immediately. It's something you'll want to revisit. And you're going to see this type of idea when you start watching the lectures. Or maybe you've already seen the lectures, and so you know that these ideas are talked about in the lecture. So now I'm going to change my share back to the lab so we can look at the assignment. And number 5 says, the chemical reaction net ionic formulas of the spectator ions. That's what this is. And in fact, this is 1, this is 2, and this is 3. Now the drawing, I'm not going to do again. 6, did the tests for the precipitation conform to expectations based on solubility guidelines? So you want to look at those solubility guidelines and ask yourself, okay, did these things precipitate because they're not mentioned in this solubility guideline? That type of thing. And number 7, what do the spectator ions for positive precipitation reactions have in common? And the answer is, well, if you look at these suckers, they're listed in the always soluble guidelines. So what do the spectator ions have in common? They're listed as soluble. All right, and that's it for this lab. And it's 7:04, which means we're done. This is due Monday. I believe. It's a very non-toxic type of lab. Nonetheless, you don't want to drink any of the concoctions. They're not going to be healthy for you. Does anyone have any questions before we leave? All right, turn your mics on and say goodbye to everybody.
Thank you.
You're welcome.
Thank you. Bye.
Hope to see you tomorrow. Bye-bye.
Later, Tony.
Bye, Greg.